Hi everyone, Dr. Burns here with our first lesson in our new chapter on chemical equilibrium. In today's lesson, we are going to be focusing on the basics of chemical equilibrium as well as understanding the equilibrium constant. So up until now, we have thought of chemical reactions as one-directional, where the reactants turn into products and then the reaction was complete. And we've brought up this term of equilibrium before, saying it can go back and forth, but we kind of ignored it up until now. So now is when we are going to explore the concept of reversible reactions, which can proceed in both the forward, which is reactants to products direction, as well as in the reverse direction, which is products to reactants. And this is often happening at the same time, and this is what we refer to as chemical equilibrium. So the true definition of chemical equilibrium is when the rates of the forward and the reverse reactions are equal, and the concentrations of the products and the reactants remain constant over time, the system is said to be at equilibrium. Now we've talked about rates before of reactant turning into product, but now we're going to be talking about the rate and how it goes from product to reactant. Understanding how to calculate that rate is the same as how we've talked in our previous lectures, but now we can see that in our image here, we can see that the rate of the formation of our product and the rate of the decomposition of our reactant, they change over a certain amount of time, and then at one point they become equal to each other and constant. This means that the forward and the reverse reactions are happening at equal rates. It's important to note about the equilibrium and the concentration, which is going to be our top image here, that when equilibrium is achieved, the concentrations of the reactants and products don't need to be equal. Instead, they just have to be constant or unchanging. Now, what does this mean on a molecular level? Well, for something to be at equilibrium, the rate of the forward and the reverse reactions are happening at the same time, which in other words can be said that as one product is formed, a reactant is then formed from that product. So it's almost like a roundabout kind of thing. So let's look at our reaction of N2O4 here. I'll try to match the colors in our image. So at equilibrium, if I had an N2O4, if I were to make an N2O4, then what would have to happen, so it would go in the forward direction to break off into an NO2. So there's our N. But it would form two of those, right? We can see how it kind of splits down the middle to create NO2, so it creates two of those. But as I create two of those, in order to maintain an equilibrium, I then have to take two other NO2s and convert them back to another N2O4. It happens at the same time. The example I like to give when I'm in a physical classroom with my students is, well, our classroom has two doors. I can only have 50 students within the classroom at any given time. So if you wanted to enter the classroom, in order for you to enter the classroom, someone else would have to exit the classroom. And it turns out that in order to do that, and I have students stand up and move themselves around so that can actually happen, is we start to see that there's this kind of roundabout way where a student walks in and a student walks out, and then a student walks in and a student walks out. And that happens over and over until I tell them to stop, because it's constant. It's constantly happening. I can't have a buildup. I'm never going to have more than 50 students in my classroom, because for every student that walks in, a student has to walk out. That's what's happening with our products and our reactants in a reversible reaction. If I make a product, I then have to reverse that reaction and make a reactant in order to maintain that equilibrium. So again, to reiterate, when a reaction is at equilibrium, the rates of the forward and reverse reaction are what's equal. So it's the rates that are equal. It's the concentrations that can be different. At equilibrium, they just have to be unchanged. And this is where I oftentimes see students get confused, is they think, well, at equilibrium, all the concentrations have to be the same. And that's not true. They can be completely different. We can have reactions where there's more reactants than products, or more products than reactants, but the reaction itself is still at equilibrium. The amount of product and reactant doesn't matter. As long as those concentrations are unchanging and the rates of the forward and the reverse reactions are equal, then we are at an equilibrium. Another big thing to remember is that at equilibrium, the reaction has not stopped. It may look like it's stopped if we were to zoom in on every atom and everything like that with our famous microscope that I keep talking about, okay? If we were to zoom in and look at that, it would almost look like the reaction has stopped because we see an unchanging number of products and reactants. But what's actually happening is they are transforming from reactants to products and back and forth and back and forth. They are doing that constantly. So the reaction has not stopped. It is just at an equilibrium. And this is something called a dynamic equilibrium, where it looks like it stopped, but it is still continuing on. Phase transitions can also be at an equilibrium, specifically when we're talking about vapors and vapor pressure. So if a liquid is placed into a closed system, the change in phase from a liquid to a gas will come to an equilibrium and will continue at a constant rate forever. A great example of this is a soda can. That's a closed system, okay? We can't let any matter in or out, but we can exchange heat, but heat isn't going to affect that too much. So what we see is that the carbonation in the soda is constantly in an equilibrium so that my soda remains bubbly. But the second that you open it, you're no longer at equilibrium because you've changed that pressure overall. You went from a closed system to an open system, so it changes everything. So when we're talking about chemical reactions and reversible reactions, we have to talk about something called the reaction quotient. The reaction quotient is noted by the variable uppercase Q. So yet another letter that's being repeated from a previous lesson, but now this is uppercase, so this is uppercase Q. Okay, it's not heat, lowercase q is heat. This is reaction quotient, uppercase Q. And the reaction quotient measures the relative amounts or concentrations of products and reactants present in a reaction at any given time. So if I wanted to look at what the reaction quotient is right when I started, I could calculate that if I knew their concentrations of products and reactants. And if I wanted to see what that reaction quotient is 10 minutes later, as long as I'm able to find their concentrations 10 minutes later, I can find what the reaction quotient is. So how do we physically calculate the reaction quotient? Well, we have to take our balanced chemical reaction into account. So for the reaction A plus B goes to C plus D, the reaction quotient can be calculated by the ratio of the concentration of the products over the concentration of the reactants. Remember, square brackets mean concentration. So for this reaction, we have the concentration of C times the concentration of D over the concentration of A times the concentration of B. So we have our products over our reactants. Each of those concentrations is raised to an exponent, and that exponent is the coefficient, the stoichiometric coefficient that we find from the balanced equation. Okay, so when we've talked about thermodynamic quantities, Gibbs, enthalpy, entropy, we used the coefficients and multiplied them by that value, but now we're going to be raising them to the exponent of the coefficient. So it's a little bit different. We're also not taking the difference, we're taking the ratio. So instead of products minus reactants, it's products over reactants. So we see C is raised to the X is its coefficient, D is raised to the Y is its coefficient, A is raised to the M, and B is raised to the N, which are their coefficients from the balanced chemical equation. So if we know the balanced chemical equation and we know the concentrations of our products and reactants at any given time of the reaction, then we can calculate Q. Now I want to note here that Q in my equation has a C attached to it. That C stands for concentration. So this is the concentration-dependent reaction quotient. So that means that you would take their concentrations into account. The reaction quotient can also be expressed for a gas, which would not be in terms of concentration, but rather in terms of pressure. So for the same reaction, A plus B goes to C plus D, instead of writing it as the concentration of each product and reactant raised to their coefficient, we now write it as capital P, meaning pressure. Specifically, the partial pressure. So we have the pressure of C raised to the X, the pressure of D raised to the Y, and mind you, the subscript of their letters is just showing you that it's the pressure of that specific reactant or product. It doesn't mean that there's no subscript that you actually have to type into your calculator or anything like that. As long as you remember to raise it to that exponent of the coefficient, then you're fine. Then it would be the pressure of A raised to the M and the pressure of B raised to the N, and that gives you the pressure-dependent reaction quotient. Which we note by Q sub P, P standing for pressure. So let's practice writing these reaction quotients. So for the following reaction, write the concentration-based reaction quotient expression. So here I have our example, just using A's and B's. Now we're going to plug in actual reactant and product formulas and coefficients. So take a moment and pause your video and try to plug in the products and the reactants and their coefficients properly for this balanced equation. So we're going to have Q sub C is equal to, let's see, I'll have my products in red and my reactants in blue, just so we know what's going where. So products go on the top, so we have the concentration of NO2 raised to the 4, because 4 is my coefficient out in front of NO2. We're going to multiply that by the concentration of H2O raised to the 6, because that's what the coefficient is out in front. And that's our numerator, because those are our only products. And our reactants would then be the concentration of NH3 raised to the 4 times the concentration of O2 raised to the 7. And that is our reaction quotient, specifically the concentration-based. Now, yes, this is gases, so we could also write this in terms of pressure, but since the problem said I want it in the concentration, then you have to abide by what the problem says. If it said it wanted the pressure-based, well, instead of concentrations, you would write PNO2 raised to the 4, PH2O raised to the 6, divided by P of the NH3 raised to the 4, and P of the O2 raised to the 7. So you could write it either way, but the problem here specifically said it wanted the concentration. So we have to write it in terms of concentration. So let's keep practicing. Let's work backwards on these problems. We want to write the equation for the reaction that corresponds to each of the following reaction quotients. So since our reaction quotient tells us about the balanced chemical equation, we know that the exponents are the balancing coefficients, and we know products are on top and reactants are the bottom. We can write out the balanced chemical equation from that Q. So let's look at this first one. Well, we know products are going to be on the top, so let's highlight that. Products are on the top, reactants are on the bottom. So, since our reactant is on the bottom, we're going to write that first. So we're going to have H2S, and we know it has a coefficient for balancing of a 2. We then write our double arrows, which show our equilibrium. Our double arrows means equilibrium. And then we're going to write our product, which is H2. That has a 2 on it, so we're going to write 2 for its balancing, plus S2 as our other product. Now there's a few things I want to note about these equilibrium equations. While the forward and the reverse reactions are happening at the same time, we still want to write it as reactants and products as if it was unidirectional. Okay, so this is still going to be our reactant, and it's still going to be on the left side of our reaction arrows, and our products are still going to be on the right side of our reaction arrows. Our reaction arrows are now just changing. Instead of a one directional arrow, we're going to have 2 directional arrows. So one arrow means unidirectional, and 2 arrows means equilibrium or reversible. So we can go in either direction. Let's do another one. So we know our reactants are on the bottom and our products are on the top. So our balanced chemical equation would start off with our reactants, which is going to be NClO2 with a 2 out in front for balancing from that exponent. We have our equilibrium arrows, and then our products, which would be NO2 with a 2 out in front for balancing from its exponent, plus Cl2. There's no exponent, so it's 1. The only thing that we don't know from Q, especially these Qs, is our reaction state or our physical state. Since, as we saw, we could have gases that can be in terms of concentrations. The only time that we would know the physical state is if we were in Q sub P, because that's specific for a gas. So Q sub P, we know they are gases. In Q sub C, we don't know their physical state. So if we don't know their physical state, then we can't write it. We would have to be provided more information. So now what I want you to do is take a moment and try these last 2 problems independently. So for C, we have Hg2 plus 4I minus is in equilibrium with Hgi4 2 minus. And for D, we have 2NOBr in equilibrium with 2NO plus Br2. And a great way to check your work on these types of problems is to double check that the reaction is in fact balanced, that you have the same number of each element on both sides of your arrows. Let's do another practice problem with interpreting these Q values. So there is something incorrect about the following reaction quotient. Correct the mistake and explain it. So what I want you to do is look at this QC expression, think about what it means for the chemical reaction, and then try to figure out what's wrong with this QC expression, and then try to fix it and explain why you fixed it that way. So if we do what we did in our previous problems, we can write out the balanced chemical equation. I think that's the best place to start with this kind of thing. So we have NO, there will be 4 of those, plus 1O2 is in equilibrium with 3 NO2s. Now if we look at our balanced chemical equation, we can automatically see that it's not balanced because I have 3 nitrogens here and 4 nitrogens there. So the problem is that this is unbalanced, so QC is not properly balanced. So in order to fix this, we would have to write out our balanced chemical equation. Okay, remember balancing is something that we've learned in General Chemistry 1, so it's not something that we should have to walk through here. So if you need to, take a second and pause your video and see how you would balance this. But the coefficients come out to 2NO and 2NO2 to give us 2 nitrogens and 4 oxygens on either side. If you were unclear on how to balance this, or seeing me balance this was very confusing, please go back and review balancing chemical equations from General Chemistry 1. It is a very important skill that we will be utilizing throughout this course. So now that I have the balanced chemical equation, I can write out the true QC, and that would be NO2 on the top with a square now, and NO on the bottom with a square now, and O2 as is. So that would be our corrected value for QC. Now let's put some numbers to these values, to QC. Let's calculate an actual number. So we said if we know the concentrations of our products and our reactants at any given time, we can calculate QC. So, in this problem, we want to consider the following reaction. Calculate the reaction quotient when the concentration of SO2, O2, and SO3 are 0.1 molar, 0.2 molar, and 0.95 molar respectively. So, the first thing that we have to do is write out the proper Q value, or Q expression, because if we don't have the proper Q expression set up, then us plugging in the numbers will not be correct. So, we know that QC is equal to products, so the concentration of the products, SO3, raised to its coefficient, which is 2, over the reactants, which is SO2 raised to the 2, and O2 raised to the 1. If you have those flipped, you just have to keep reminding yourself that it's products over reactants. So now that we have our Q expression, we can plug our numbers in. So the concentration of SO3 is the third one here, 0.95. And we are going to make sure to square that. And we'll divide by our reactant concentrations of 0.1 and 0.2. So SO2 is 0.1, which we will make sure to square. We'll multiply that by 0.2. which we don't need to square. So let's pull out our calculator so that we can solve this problem together. Okay, so we can take that 0.95 and we can square that, and we can divide by, I'm just going to use my parentheses very properly here, 0.100 squared times 0.2 end parentheses, just to make sure I'm not multiplying 0.95 over 0.10 squared or anything like that. Just to double check and make sure my math is correct. And again, if that doesn't make sense to you, then take it one step at a time. Calculate the individual values and then do your multiplication. Take it step by step. So this gives us a QC that is equal to 451.25. And that with sig figs is going to be 451. Now it's very important to note here that QC is unitless. QC and what we're going to be relating it to later in our lecture are all unitless quantities. We could technically look at the molarity squaring and everything like that, but overall QC is typically unitless, as is QP. Any expression for Q is going to be unitless. Okay, let's do one more practice before moving forward. And I bring forth this practice problem because Alex, your Alex homework, likes to show things in terms of grams and liters or moles and liters to make you calculate these concentrations. So determine the value for the reaction quotient for the following reaction. A mixture in a 5-liter flask contains 3.85 grams of SbCl5, 9.14 grams of SbCl3, and 2.84 grams of Cl2. So we're given masses and a volume. So in order to find the concentrations for our Q, we are going to have to calculate their molarity in that flask. So we need to go from grams to moles using molar mass, and then we need to find molarity. So the first thing that we can do before we do that is set up our Q. So QC is going to be equal to the concentration of our products, SbCl3 times Cl2 over our reactant of SbCl5. So what I want you to do now is pull out your periodic tables so that you can calculate the molar masses of all of our products and our reactants, so that you can convert from grams to moles for each of these values. And if you don't remember how to do that, or you're not confident in that, please go back and review that from General Chemistry 1. So let's keep in mind that if we wanted to find moles, we would have to take the mass and divide it by the molar mass. And that would get us out moles. And if I wanted to find molarity or concentration, I have to take moles over volume, and that volume must be in liters. So off screen, I calculated these concentrations for my products and our reactants. Please make sure that your values match mine, and if they don't, go back and recalculate those molar masses, those mole values, those concentrations to make sure they are the same as mine. So my concentration of SbCl5 is 0.00258. Concentration of SbCl3 is 0.00801. My concentration of Cl2 is also 0.00801. So now that I have those concentrations, I can plug them in to solve for QC. So QC is equal to my products, so 0.00801 times 0.00801 divided by my reactants, 0.00258. So we can calculate that, 0.00801 times 0.00801, and we can divide that by our reactants, 0.00258. So we get a QC that is equal to 0.0249. and it's unitless, so we just leave it as is, and it's 3 significant figures. So what does that value of QC actually mean? When I say, well, QC is 0.0249, but in our previous problem it was like 400, what does that magnitude tell us? Well, the reaction quotient, the value that it is, tells us the state of the reaction at any given time in the reaction itself. Therefore, the numerical values will vary prior to achieving equilibrium. It'll constantly be changing as those concentrations of products and reactants are changing until we get to equilibrium. So, the reaction quotient serves as a useful indicator of the reaction status. So let's consider our reaction of SO2 and oxygen creating SO3. We know we found the QC for this before, okay? So let's think about what happens, or what the QC would be right at the beginning of the reaction. Well, right before the reaction starts, let's say all I have are reactants. So I only have SO2 and O2. No matter what their concentration is, I only have those two. The concentration of my product, SO3, its concentration before the reaction starts is 0. So we can plug that 0 into our QC expression, and automatically, no matter what those concentrations of SO2 and O2 are, no matter what they are, they could be really high, they could be really low, it doesn't matter, because right at the beginning of the reaction I have no product. And therefore the concentration of my product is 0, and when I do 0 divided by any number, that value comes out to be 0. So QC is 0 right at the beginning of the reaction. Therefore, as we proceed through the reaction, we know that QC is going to increase as we go through the reaction. QC can't be negative. It can be really small, but it can't be negative. So now let's think of us as proceeding through the reaction. So as the reaction proceeds, the reactant concentrations will start to decrease, as we can see in our image here. We can see that our reactant concentrations are starting to decrease. There's our SO2 and our O2. They're starting to decrease, and we see that the product concentration is starting to increase. So there's SO3 in yellow. So therefore, the reaction quotient is going to start to increase, because we're going to start having numbers on top and on bottom, making a reliable ratio that is greater than 0. As the reaction proceeds through more and more time, the reaction is going to at some point reach an equilibrium. And at that equilibrium, the concentrations are going to become constant, as we see from our image up here. Our concentrations are constant. Therefore, Q becomes constant as well. So Q is going to be the same at this point in the reaction as it is at this point in the reaction, because the concentrations are unchanging, which is one of our requirements for a reaction to be at equilibrium. The concentrations are unchanging. They don't have to be equal to each other, they just have to be unchanging. What I don't have an example of here is, what if we started with only product instead of only reactant? So let's say we have this QC and all we have is a concentration of SO3. We start with only products and I have no reactants. So QC, the expression would be, well, I have a concentration of SO3, doesn't matter what that concentration is, but the concentrations of SO2 and O2, if I only had product, would both be 0. So this would be 0 squared times 0. And we know through math that anything when you divide by 0 is going to be infinity, or an unknown number. Infinity is usually what we go with. So QC can range from 0 to infinity. Infinity would be if I only had products. The only thing that I can do is create reactants and start to decrease my QC. So if I start with reactants, my QC is going to increase, and if I start with products, my QC is going to decrease. So now let's talk about what QC means at equilibrium. Well, we've said that when a reaction is at equilibrium, the forward reaction and the reverse reaction are occurring at the same time. And when the reaction is at equilibrium, Q is unchanging. So when we are at equilibrium, Q is now considered something called the equilibrium constant. So we went from the reaction quotient to the equilibrium constant. So the equilibrium constant is denoted by the variable K. Here's another variable that we've used in the past in previous lessons, and now it means something different. So uppercase K is going to be our equilibrium constant. Lowercase k was our reaction rate and Boltzmann's constant, whereas uppercase K is going to be our equilibrium constant. So we use K when we reach equilibrium for a given reaction, and Q is used at any other time. So if the problem says we are at equilibrium, then we are thinking of K. If the problem states that we're outside of equilibrium or we're not at equilibrium yet, then we use Q. K is set up the same way as Q, so K is equal to the concentration of products raised to its coefficient over the concentration of the reactants raised to its coefficients. But to denote that it's at equilibrium, you'll sometimes see that concentration notation change by adding an EQ as a subscript to say that that's the equilibrium concentration. We sometimes often see Q as, or K written as KEQ as well, just to remind us that this is an equilibrium constant. So we can use Q and K together. We can predict the direction the reaction is going to proceed in order to get to equilibrium by comparing our values of QC and KC, or K. Remember, C just stands for concentration. So we can compare the Q of concentration to the K of concentration. We can compare the Q of pressure to the K of pressure. Okay? So we remember that if we start with just reactants, Q is going to be equal to 0 and must increase. And then we said if we had products only, Q is going to be equal to infinity, and it must decrease. So if we think about our reactants only, the only way that the reaction can get to equilibrium is by increasing. So Q is automatically going to be smaller than K. So when Q is smaller than K, in order for the reaction to reach equilibrium, the reactants must be converted to products, right? Because that's how Q is going to be increasing. We're starting with only reactants, so the only way to get to equilibrium is to produce some products, and therefore we are moving towards our K value. So the reaction is going to proceed in the forward direction, where we're going from reactants to products. When Q is equal to K, that's going to be at equilibrium. So the concentrations referring to Q are at the same concentrations as at equilibrium. So when Q is equal to K, we are at equilibrium. Now if we take our products only example from earlier, Q is infinity and the only way it can go is down. It has to decrease. Therefore, it's going to be greater than Kc, or K. So when Q is greater than K, in order to reach equilibrium, the products must be converted to the reactants. So the reaction is going to proceed in the reverse direction. So we're going products to reactants. Because the only way it can go if Q is really large in comparison to K is downward. or in the reverse direction, products to reactants. So let's put some numbers to that to really kind of cement in the concept. So consider the following reaction and the starting concentrations of products and reactants for 2 experiments. For each experiment, determine which direction the reaction proceeds as it goes to equilibrium. So we have here our equilibrium constant K, and what we are going to be doing is taking each experiment and finding Q. So we're going to do that twice. So we're going to find Q. We're then going to compare Q and K to see if it's larger or smaller so that we can see what direction we are going to be going in that reaction. So let's do the first experiment together. So in order to find Q, we have to take our balanced chemical reactions and write our Q expression for that. The first step is always finding the proper Q expression. So we have products of CO2 and H2, which we're going to multiply together, divided by our reactants, CO times H2O. So now that we have our Q, we can plug numbers in. So in experiment 1, the concentration of CO2 is 0.0040, and the concentration of H2 is also 0.004. We divide that by our reactant concentrations, which are both 0.02. So let's grab our calculator so we can solve this problem together. So we have 0.0040 times 0.0040, and we divide that by I'm going to put some parentheses in there, 0.020 times 0.020. And we get out a Q value, QC, because it's concentration based, is 0.04. And again, that's unitless, so there's no units on that. Now we're not done yet because we want to first find Q and then compare it to K. So K is 0.64. So we know that 0.04 is less than 0.64. So QC is less than KC. So if we look at our table from our previous slide, if Q is less than K, then the reaction is going to proceed in the forward direction because we're going to take all of those reactants and create product. So this is going to go in the forward direction. We oftentimes refer to it as like left or right, so this would be moving to the right. I believe your ALEKS homework uses both terminologies depending on the problem that it's asking. Sometimes it says, is it going forward or reverse, or is it going left or right? So forward is moving to the right because you're moving to the products. Right is the product side. And if you were going in the reverse direction, you would say you are moving to the left. So they're kind of interchangeable. So just keep that in mind. So now what I want you to do is do the same calculation that we did in our previous problem, but now do it for experiment 2. So for experiment 2, right here, we want to find Q. So we're going to plug in those variables to our Q expression, find Q, and then compare it to K to determine the direction that the reaction is going to go in. So we can plug our concentrations in just like we did in our last problem. So Q is equal to 0.037 times 0.046 divided by 0.011 times 0.0011. So we'll take that calculation, 0.037 times 0.046, and divide that by 0.011 times 0.0011. Remembering to get those zeros correct in there. So Q is equal to 141 with sig figs. So Q 141 is greater than K of 0.64. So if Q is greater than K, then we are going in the reverse direction. And this means that we are moving to the left. We are creating reactants. Okay, let's do one more practice problem before moving on. So the initial concentrations are given for the following reaction. Calculate the reaction quotient Q and determine the direction the system will proceed in. So forward, reverse, left, right, determine that. So pause your video and solve for Q and determine the direction of the system. The first thing you want to do is write your Q expression. So Q is equal to products, concentration of N2 times the concentration of H2, making sure to raise that H2 to the 3 because of the coefficient out in front, divided by the reactants, which is NH3, raised to the 2 to account for its balancing. So now we can plug in our numbers. We know N2 is 0.904. We know H2 is 154. We're going to cube that, divided by our reactant of 0.20, which we are going to square. So let's take that. I'm going to do it steps at a time. 1.54. I'm going to cube that, and then multiply that by 0.904, and then divide that by 0.2 squared. And I get a Q of 82.54. Now Q is then greater than K because Q is 82.54 and K was 17. So when Q is greater than K, this is moving in the reverse direction. Or it's moving to the left. Okay, so along the same lines of what do the values of Q mean, what does the value of K tell us? K tells us when we're at equilibrium. We know if we see K, we're at equilibrium. But what does the magnitude of that number mean? Well, K is now going to tell us the extent at which the reaction will proceed. How much products will there be in relation to the reactants? We can tell that information from our K value. So we can deduce 3 possible scenarios when we are looking at a K value. First, being that the reaction goes almost to completion, so we have more products at equilibrium than reactants. This means that K is going to be very large because our concentration of products is going to be a large number. I'm going to have more products in comparison to reactants, so it's going to be a large number over a small number, which would then give us a large value for K. That ratio would be very large, greater than 1. So when we say that K will be large, we specifically mean that it's going to be greater than 1 times 10 to the third, or 1,000. So if K is larger than 1,000, then we're mainly going to have products at equilibrium. On the opposite side, the reaction does not occur significantly is another possible scenario, so we have more reactants at equilibrium than products. So instead, if we have more reactants, then our denominator is going to be large, and our numerator is going to be small. We don't have a lot of products, but we have a lot of reactants. So that means if I have a small number over a large number, K is going to be small, meaning I have more reactants at equilibrium. And when we say small, we mean less than 1 times 10 to the negative 3, so 0.001. So less than that number would be that there are more reactants at equilibrium than products. The third scenario is everything in between. The reaction proceeds modestly, so there are about equal amounts of products in our reactants. So we can say this as, you could have a large number over a large number, or you could have a small number over a small number. They each give you a ratio that is pretty close to one another. So the K value for this would range between our two extremes, so between 1,000 and 0.01 or 0.001. So if it's within that range, then we can assume that there are about equal amounts of products and reactants at equilibrium. So that's what the magnitude of K tells us. We're going to find this especially useful in our future lessons when we start calculating concentrations at equilibrium using a K value. We're going to find this concept very useful to us. So let's talk a little bit more about those equilibrium expressions, or those K expressions, products over reactants. So when we're exploring reactions at equilibrium, we have to take their states into account. We said earlier with Q and QC and QP that we don't always know their physical states from their expressions. If we were just looking at a QC expression, we don't know their states, which means we don't know the full information about that balanced reaction. So, and this is because, specifically, only gaseous species and aqueous species appear in equilibrium expressions. Pure solids and pure liquids do not. So if I'm only given a QC or a KC expression, I don't know everything about that chemical reaction, because what if there was a solid in there? What if there was a pure liquid in there? It would not show up in the QC or the equilibrium expression. And this is specifically because solids and pure liquids don't have a concentration that would change. Okay, how do you find the concentration of a solid? We can't, because concentration is defined as moles per liter. But we don't have a liter value for a solid, because it's not a solution. So when we're looking at equilibrium expressions, we only take gaseous species and aqueous species into account. So we have to remember the difference between our physical states. Remember, AQ is aqueous, pure liquid is going to be L. And we've said in the past, back in General Chemistry 1, that the only pure liquid that we're really going to be looking at is going to be H2O. Now, if you see H2O in a balanced equation, it does not mean to ignore it. You have to look at it at its physical state, because if it's H2O gas, water vapor, that has a concentration. That's a gaseous species, so we would count it. But if it's H2O liquid, then we don't count it. So you have to pay attention to the physical states. So, when the products and the reactants are in the same phase, gaseous solution, aqueous solution, the equilibrium they create is considered a homogeneous equilibrium because they are in the same phase. So these reactions take place specifically in solutions, both gaseous solutions and aqueous solutions. So we see here from our multiple examples, we have AQ, AQ, and AQ. They're all the same phase. We have AQ, AQ, and AQ again. I don't think I have any gaseous ones here. We'll do that in our next slide. But I do want to point out two specifics in our last two. We have water as a reactant in both of these reactions. Now, aqueous still means it's in a solution, and water can be part of the solution, but water as a pure liquid would not show up in our Kc expression. So we can see here that Kc's, they don't have water in them. There's no H2O in their denominator because H2O is a liquid. Okay, I have my liquid here. And we don't consider liquids when we're writing out equilibrium expressions. So we see that they don't show up in the denominator there. They can still be part of the balanced chemical equation, but they are not a part of the equilibrium expression. So this shows exactly what I was saying before, that we can look at a QC or a Kc expression and we still don't know everything about that balanced chemical equation because of the fact that there could be other states present, like a solid or a liquid. So if you were to only be given these Kc's and you tried to write their balanced chemical equation, well, you would have HF in equilibrium with H3O plus and F minus, but that's not balanced. So when we're looking at these, we don't know everything about that reaction. Let's go a little bit further into gas phase homogeneous equilibrium. So gas phase solutions can be expressed either in terms of their molar concentrations, which would be square brackets K sub C, or, I should say or their partial pressures, that would be like P values or K sub P. And that just depends on what values are provided in the problem. So here I have a bunch of gas examples, homogeneous equilibrium, so they're all gases. I have gas, gas, gas. We see that they're all in the same phase. So since they're all gases, these Kc's can also be written as Kp's. So it'll just be the pressure of C2H4 and the pressure of H2 over the pressure of C2H6, and so on and so on. Okay, so they can all be written in terms of their pressures as well. But what we can't say is that Kc and Kp are equal to each other. They are not equal to each other. Concentrations and pressures are not equal to each other. They can be related to each other. We can relate Kc and Kp to each other, but we cannot say that Kc and Kp, those two expressions, are equal to each other because they're not. Look at the units. Molarity does not equal ATM for pressures. Okay, they don't equal each other. Now we can relate those two values, so the two terms Kc and Kp can be related through the ideal gas law, which we looked at in an earlier chapter in General Chemistry 1. So we can relate it through the ideal gas equation and the definition of molarity. So here we have our ideal gas equation, PV equals nRT. Okay, now molarity is equal to moles over liters or moles over volume, which we have those variables in our PV equals nRT. So I can take this PV equals nRT and rearrange it to get moles over liters together, right? If I divide P over V by V, I can take N over V. And essentially what I can do is I get P is equal to N over V times RT, also known as M for molarity times RT. Remembering that R is the ideal gas constant, which we've used in our previous lessons, and T is the temperature. So if we know the concentration, we can take that value and multiply it by RT and get the pressure instead, because molarity has units of moles over liters. R has units of liters times ATM per mole Kelvin, and temperature has units of Kelvin. So if we look at what cancels, mole cancels, liters cancel, Kelvin cancel, and you're left with ATM to get a pressure. So if you know the concentration, you can multiply it by the temperature and the ideal gas constant in order to get the pressure. And that's how we can relate Kc and Kp. So let's look at how we can do that, because it is a couple of steps to get there, but we can find an equation that relates both of those together. So if we know that the pressure is equal to mRT, and we know that a Kp expression is the pressure of C raised to the x, the pressure of D raised to the y, the pressure of A raised to the m, and the pressure of B raised to the n. Okay, we've defined that earlier in the earlier part of this lesson. If we know that P is equal to mRT, we can just take that and plug it in. So it's the concentration of C times RT raised to the x, the concentration of D times RT raised to the y, over the concentration of A times RT raised to the m, and the concentration of B times RT raised to the n, which is exactly what we see here, but I'm just showing concentration in square brackets. Okay, so RT isn't going to vary when we're looking at pressures. Okay, RT, R is a constant, T is going to be constant for that reaction. Okay, we're going to assume that that temperature is not changing. So what we can do is we can factor out the RT. So that's what we're doing in this next step. We're factoring out RT as well as its raising to the coefficients. So we see we get our Kc expression here. Okay, we know that that's equal to Kc because concentration of the products over the reactants raised to their coefficients is equal to Kc. Then we have our factored out RTs also raised to those exponents, right? Because if we were looking at the exponents, they apply to the RT as well as to the concentrations. So this is how it factors out. So we can then simplify that. We know that Kc is here, RT over RT is RT, and the only change that we have to make is raising that RT to those coefficients. We still have to take the coefficients into account. We still have to make sure that they are there to account for the balanced chemical equation. Okay, so we then define this term of our coefficients, the difference in our coefficients of reactants to products, as delta N. Now we've calculated delta N in some of our previous lessons when we've looked at entropy. We've taken S is equal to S of the products minus S of the reactants when we were looking at the number of moles on either side. So we take the moles of product minus the moles of reactant. We just added up the number of moles on the product side and subtracted off the number of moles on the reactant side. That's exactly what delta N is. It's the same value, because X, Y, N, and M are all coming from our coefficients in our balanced chemical equation. So we've calculated delta N before. So our relationship between Kp, we said before that Kp cannot equal Kc. Okay, we said that's not possible because we can't relate concentrations and pressures directly. But instead, now that we have our ideal gas law, we can write that Kp is equal to Kc times RT raised to the delta N. And mind you, that delta N is only applied to the RT because all of the coefficients are accounted for in Kc. So if you know Kc, if you know the value of Kc, you can then use that to solve for the value of Kp, or convert it to a value of Kp. So let's look at how we can use that. So for the following reaction, the Kc is equal to 0.28 at 900 degrees Celsius. What is Kp at this temperature? So we know Kc. Kc is given to us, it's 0.28. We know R. It's given to us as 0.0821. This R is different than the R we used in previous chapters, specifically because of the units that we need. So this is the R that we used in the ideal gas law chapter back in General Chemistry 2, and this is specifically in units of ATM. If you were asked for a different pressure unit, you would have to use a different value of R for that pressure unit. This is not the same R that we used in our kinetics chapter. They are different values. They come from the same thing. They're both the ideal gas constant, but they just have different units, okay? So we have to pay attention to our units. So R here is 0.08201 liters times ATM per mole Kelvin, okay? We need our temperature. Our temperature is given as 900 degrees Celsius, but we need to convert that to Kelvin. So we're going to add 273.15 to get our temperature. And then we need to find delta N. So remember, delta N is just the moles of product minus the moles of reactant. So we have 3 moles of product, right? 2 plus 1. There's a 1 in front of that CH4. Minus 4 plus 1, which is 5. So 3 minus 5 is minus 2. Yes, you need to make sure you get your sign correctly. If you haven't noticed up until this point with all of our lessons, always our signs matter. So watch your sign there when you're calculating delta N. Okay, so now that we have all of our variables identified, we can calculate our T and solve this problem. So let's grab our calculators out so we can solve this together. So let's take 900 and add to that 273.15. Oops. So we get that our temperature is 1173.15 Kelvin. So let's plug everything in. So we want to find Kp, and that's going to be equal to Kc 0.28 times R, which is 0.0821, times T, 1173.15, raised to the minus 2. Now here's where you want to just make sure you're getting everything into your calculator correctly. This negative 2 only applies to what's in the parentheses, the R times the T. So we are going to take that 0.0821, multiply it by that temperature, and then we will raise that number to the minus 2, which we will then multiply by 0.28. Okay, that minus 2 does not apply to that Kc value, so you can't take all 3 of those values, multiply them together, and then raise it to the negative 2. It will not get you the right answer. So this gives us a Kp of 3.0 times 10 to the minus 5, and again, that is a unitless quantity. So we've taken a Kc and we've converted it to Kp using R, T, and delta N. Let's have you try the next one. Here we want to convert the value of Kp to Kc, so we're doing the opposite of what we did. We're given Kp, we're given our temperature, we have our balanced equation, here's our R again. Now we want to find Kc. So take a second and pause your video and solve this problem for Kc. So let's define our variables. We have Kp, that's 4.08 times 10 to the minus 25. We have R is given as 0.0821. We have T as 25 degrees Celsius, so we'll add 273.15, that's 298 Kelvin. And finally, we have delta N, which we get from the balanced equations. We have products, 10 and 1, that's 11, minus, this is a hydrate, so this counts as 1. Okay, there's no plus sign separating that, so that counts as 1. So 11 minus 1, so that's a delta N of 10. So We can now plug everything in, simplify, and solve. So we have 4.08 times 10 to the minus 25 is equal to Kc, which we're looking for, times R, 0.0821, times the temperature, 298.15, raised to the 10. So let's simplify and solve. We'll take that 0.0821, multiply it by 298, our temperature, and raise that to the 10 power. We will then simplify and solve for Kc by taking 4.08 times 10 to the minus 25 and dividing it by that answer that we just got to get a Kc value of 5.28 times 10 to the minus 39. So a really small number. K, Q, all those values, they can be really small, they can be really large. The only thing they can't be is negative. So just keep that in mind. Okay, so our conversion between Kp and Kc is specifically for when we have reactions where gases are involved or when they're all in the same phase of gases as well. But what if they're in different phases? So as we previously stated, solids and pure liquids do not contribute to the overall equilibrium of the system, and K only takes into account gaseous and aqueous phases. So if it's a G or an AQ, we put it into the K expression. If the reaction includes products and reactants of different phases, it is referred to as heterogeneous equilibrium, and the expression for K only takes into account gases and aqueous components. So here we have a few examples of that. We have PbCl, that's a solid, and we have Pb2 plus and Cl minus, where we have AQs. So the PbCl solid we just ignore because it's a solid. So we can see that our Kc only takes into account our aqueous products. The same thing goes for our second equation, where we have calcium oxide as a solid, CO2 as a gas, and calcium carbonate as a solid. Kc only depends on that gas. And we can see that more with our other two examples, again with our solid and our liquid being ignored in our Kc expressions. So for our last practice problem, let's practice writing out those equilibrium expressions and then solving for Kc with some values. So here we have the equation CO2 gas plus carbon solid is in equilibrium with carbon monoxide gas. We want to first write the Kc expression or equation, and then if the concentrations of CO2 and CO are 0.150 and 0.250 at equilibrium, calculate Kc. Well, we know that Kc is only going to take into account gases and aqueous solutions, so we can just ignore that carbon solid. It is not going to contribute to our Kc expression. So then we go about and follow our usual rules of writing out Kc of products over reactants. So we have our concentration of our product, carbon monoxide, making sure to square it to account for that 2 out in front. And then as our reactant, we have CO2. It has a 1 out in front, so we don't need to raise it to anything. So that's our Kc expression. And now that we know the concentrations of those, we can plug them in. So CO has a concentration of 0.250, so 0.250. We're going to take that value and square it and divide it by the concentration of CO2, which is 0.150. So we can use our calculators, 0.250, we're going to square that, and then we're going to divide it by 0.150. And we get a Kc value of 0.417, 3 sig figs for that. So that is our Kc value for that expression.